Let's look at some of these announcements. Your jet impact reports today due in lab today. And then we're going to begin kind of like the pinnacle lab of the semester today. It's a two-part lab. I've given you the handout for it. In the first part, you're going to design an experiment. And in the second part, you're going to conduct the experiment. So if we have a bit of time at the end of the class, I'll circle back and address the lab a little bit more. But we're all meeting at 2 o'clock today. Both groups meet at 2. And we'll talk about this big design of a lab thing that we're going to do. Your next homework assignment 5B is due on Thursday. And some of you who looked on our class webpage may have noticed that there's already recordings for class 23 and 24. Those are next week's lectures. We're not going to meet in class next week. We're going to have recorded lectures for both Tuesday and Thursday next week. And I'll talk more about that on Thursday. I already have the handouts for you. Everything's all set up for those class meetings. And you're going to submit your homework assignments next week in the same way that you did on Thursday. You're just going to put it into an envelope and the grader will pick it up and we'll start grading it, even though I'm gone. So more information about that on Thursday. Any questions about these announcements that are on the screen? All right. Well, we're going to start with a in-class exercise where I'd like you to collaborate with your classmates to do some calculations. And here's a picture of a reservoir in South Carolina. And this picture was taken several years ago when South Carolina was experiencing some of the worst drought conditions that it has ever been on record. Maybe they've been worse in the past, but nobody was around to measure it. Things are fine now in South Carolina. The drought's over there and the lakes are back to its normal level, but in much of the United States, the droughts are as bad as ever. So this is a really good opportunity, considering reservoirs, to apply the principles and practice the principles of continuity. So I'm going to give you a handout that I'd like you to work on collaboratively with another student, and I'm going to collect one solution from each of you, but I'd like you to write the name of the person that you worked with on the handout. This is going to count as a couple of homework points. Like I do when we have an in-class exercise, I'll give you some homework credit for completing this, but it's in a way similar to the quiz that we just completed in terms of considering the mass flow rate, rates of accumulation, and what that does to the water levels. Okay. So we'll do a couple more of those in-class exercises through the semester. I think it's useful for you to collaborate. When I first started teaching, I kind of felt like if I didn't talk for the whole 75 minutes, it was like the students were somehow getting shortchanged. But I think really students probably learn more if the professor talks a little bit less. It's hard to pay attention for 75 minutes straight. So I like doing these just because you can learn from each other as effectively or maybe more effectively than you can learn from a lecture. Let's look at a couple of those combo problems I mentioned that we do, where we combine continuity equation with Bernoulli's equation. And that's one of the most common combinations that we do. And here's one where we are connecting a manometer, differential manometer, to a nozzle. And we're going to have to use the continuity equation here to find out what is the deflection in the manometer fluid between the two surfaces that are shown there. All right, so it's air that's going through the nozzle with a density of 1.03 kilograms per cubic meter. And the manometer fluid that we're using has a unit weight of 15,710 newtons per cubic meter. It tells us that the cross-sectional area at 1 is double the cross-sectional area at 2. So A1 is equal to 2A2. We're going to use that to solve for the velocities. For example, if the velocity at 1 is 30.48 meters per second, which is given there, that means that the velocity at 2 will necessarily have to be double that, because A1 V1 is equal to A2 V2. And so if the area at 1 is double the area at 2, then that means that the velocity at 2 has to be double the velocity at 1. So V2 is 60.96 meters per second. By the way, for the air, if we calculate the unit weight of that air, it's just simply multiplying the density by G. So 1.03 kilograms per cubic meter and 9.81 meters per second squared. So 10.104 newtons per cubic meter. Okay, so this is a combo problem where we're applying Bernoulli's equation, and then we're going to apply it to the manometer equation. So Bernoulli's, written in terms of pressure, P1 plus gamma Z1 plus the density of the fluid, V1 squared divided by 2, is equal to P2 plus gamma Z2 plus the density, velocity, 2 squared divided by 2. So if we look at this, we can see that the elevation difference between 1 and 2 is given. And we're going to rearrange the terms to be in terms of piezometric pressure. And we've talked about before how P sub Z, piezometric pressure, is pressure plus gamma Z. And using piezometric pressure implies that we've selected some location to be our vertical datum. And so we're saying, for the purposes of this problem, let's choose a point and measure all of the elevations relative to that point. And in this case, it seems like a likely thing that we'd want to select maybe location 1 as our vertical datum. But what we'll do is we'll say P sub Z1, and that P sub Z1 is grouping together P1 plus gamma Z1, and add the unit weight velocity 1 squared divided by 2 is equal to P sub Z2, where we did the same thing there, combining P2 plus gamma Z2 plus density velocity 2 squared divided by 2. Now, we know from the manometer equation that what this manometer is measuring is a change in piezometric pressure. It's not just the pressure that it measures, but it measures the pressure relative to the difference in elevation, because there would be a difference in pressure simply because this is vertically oriented. You know, location 2 and location 1 will have a different pressure because location 2 is higher in the fluid than location 1 is. That's the hydrostatic equation. But what this differential manometer does is it automatically cancels out and accounts for the difference in elevation, and it measures instead the piezometric pressure, which is the pressure difference relative to the change in elevation. So what we're doing in Bernoulli's is sort of combining things so that we can express it in terms of the change in P sub Z. So what we're saying is, if we continue this expression, is delta P sub Z is going to be the density of the fluid divided by 2, and then the difference in velocities. Okay, so move P sub Z over here. So delta P sub Z is P sub Z 1 minus P sub Z 2. And we move the velocity term over to the right-hand side of the equation. And this is what we've got for our P sub Z term. And if we substitute in the actual values for that, the density is 1.03 kilograms per cubic meter divided by 2. And the difference in velocity is 60.96 meters per second squared minus 30.48 meters per second squared. The delta P sub Z is 1435 newtons per meter squared. Let me ask a conceptual question. What would be the delta P sub z if there was no air flowing through the nozzle? If it was just static conditions, what would be the delta PZ? It would be 0. That was a good guess. There would be no change in piezometric pressure. There would be a change in pressure between 1 and 2, but that would only be because of the static hydrostatic equation. But it's when the air is flowing and there is a change in pressure either due to compression of a gas or energy loss or Bernoulli's equation. In this case, we're assuming that since we're applying Bernoulli's equation, that between 1 and 2 there's no energy losses, because remember, Bernoulli's equation says assume an inviscid fluid, and so if it's an inviscid fluid there's no energy losses. So here, this delta P sub z, this exists only because there's air moving through the nozzle, and the pressures are changing because of Bernoulli's equation. This tells us how much the piezometric pressure is changing. So let's do the other part of the problem. That is to look at conditions in the manometer. And the manometer, even though inside the nozzle there's fluids moving around, there's gases moving from 1 towards 2, inside the manometer conditions are static. So in the manometer, things are in equilibrium. That change in piezometric pressure caused this liquid level to go down because there's more pressure in here than there is up top. By the way, does that make sense? Why is there less pressure at 2 than there is at 1? We can just see by inspection, just looking at it, the fact that this elevation is lower means that the pressure at 1 is kind of like pushing down on that side. And think like if it was a solid or on some sort of like a string, or I don't know. If you're pushing down on it, it would go up over here. And so that's, visually we can see that the pressure at 1 is bigger than the pressure at 2. Why? Why is the pressure at the big section of the nozzle higher? It's the change in velocity. Low velocity, high pressure. Then up here at 2, there's a higher velocity and a lower pressure. Remember, there has to sort of be a balance. You're exchanging velocity and pressure in a nozzle like this. And we saw that in the lab when we did the Bernoulli experiment, that the piezometer levels went down in the contracted throat of that venturi because the velocity was going up. So that's why that deflection is there. The manometer equation tells us, as it's written on the screen there, that delta P sub z is delta H multiplied by the difference in the unit weights. The liquid unit weight, meaning the manometer fluid, minus the air. We can rearrange that expression to solve for the delta H. It's delta P sub z divided by the unit weight of the liquid minus the unit weight of the air. So the delta H is 1435 newtons per meter squared divided by 15,710 newtons per meter cubed minus 10.104 newtons per meter cubed. That works out to a delta H of 0.0914 meters. So that'll be the delta H. So we're in chapter 5 now. That's continuity. Where was the continuity in this problem? Where did we use the continuity equation? Bernoulli's was chapter 4. Hydrostatic equation, that was chapter 3. That's right. Exactly. Yeah, the continuity part of this was right at the beginning. It was finding out what is the velocity at 2. So in this nozzle, flow in equals flow out. In this nozzle, there is no accumulation of air. There's no like storage mechanism. It's just we knew that the velocity at 1 was given, so that's how we calculated V2. All right, any questions about the example? Let's talk again about boiling. You can boil water, as we've talked about before, by heating it. And the other way you can boil it is by reducing the vapor pressure, reducing the pressure above the liquid. So vapor pressure is just the pressure at which a liquid will boil. And if you increase the temperature, then that increases the vapor pressure. And that's why water boils at 100 degrees Celsius, is that the pressure of the water is equal to atmospheric pressure once you get to 100 degrees Celsius. So you'll notice 760. You may remember that one of the ways that you can express atmospheric pressure is pascals, which is 101,325 pascals is atmospheric pressure. Or if you convert that from pascals into millimeters of mercury, it's 760. So the higher the temperature is, the higher the vapor pressure is. Atmospheric pressure boils at 100. And then the other way to get water to boil is by reducing the pressure around it. We watched the YouTube video of when they were pumping the air out of a glass jar and how the water was boiling as the air was evacuated from that glass jar. Do you remember why that eventually it turned into a solid brick of ice? Because at the end, after it was boiling, at the end they took that glass jar off, and it was a solid, that water that had been boiling earlier was now solid ice. Do you remember why it did that? It's because when things go from the liquid phase to the gas phase, they give off heat. And so, let's see, have I said that right? Yeah, from the liquid phase to the gas phase, they are trying to absorb heat. So, has anybody here ever recharged the air conditioning in their car, you know, like with the little cans of Freon that you can buy at the auto store? If you've ever done that before, like when you screw it into the hose and you connect the hose to your car, the can gets really cold. As you start putting the Freon into your system, the can gets really cold because what it's doing is it's taking that liquid Freon and it's turning into a gas that's going into your system. And so anytime something goes from a liquid to a gas, it requires energy to do that. You have to give it energy. And so in that vacuum bell, there wasn't enough energy going into the water to sort of counteract the vaporization that was happening, and so it froze because all of the energy was being released from that liquid water as it went through the transformation. That's kind of a side tangent. What we're really talking about today is cavitation. So we've already talked about Bernoulli's equation. Let's think about a tank of water. We only see part of the tank over here. You know, there's water, free surface of water. We go down through the water, and then here's a pipe that's coming off to the side of the tank. So water comes from the tank and it goes into the pipe. And it's moving slowly through the pipe because this is a pretty big diameter pipe, so it's not moving very fast. But then there's a contracting section, and the velocity increases considerably as it goes through this narrow section. We just were talking about how Bernoulli's equation tells us if the velocity goes up, the pressure goes down. And that's what this dashed line is. This dashed line is a graph of the pressure expressed in terms of piezometric head. So it's the water level that the water would go to that level if we put a hole in the pipe and connected a tube. The water would rise to that elevation. And it's a reflection of what the pressure inside the pipe is. So if we have a slow velocity, like relatively low flow rates, that would maybe be the top line. You know, if you start off with a slow velocity, then it goes like a medium velocity, and then it's slowing down again. So this top line is showing that the pressure is high, goes down a little, but then the pressure recovers again. The middle line is, what if you had a higher flow rate than that? Well, the pressure would go lower, and then it would go back up again. When the velocity started slowing, that extra velocity would be exchanged again for pressure. This bottom line is saying, what if you had a really high flow rate going through the pipe, and so that you have a pretty high velocity to begin with through the large section of the pipe, but then when it goes through the contracted throat of the pipe, the velocity is really high. And what that does is it actually brings the pressure so low that now the pressure is approaching the vapor pressure of the liquid. In other words, it's a negative gauge pressure. There's no such thing as a negative absolute pressure, but there is a negative gauge pressure. Do you remember in the early part of the semester when we were talking about pressures, how we said that there are two different lines that we sometimes measure pressure relative to? The vacuum of space is one of our datums, and that's where we measure like absolute pressure from, is measuring from the vacuum of space. When we use our atmosphere as the measuring point, then the gauge pressure is what we're talking about there. So here, what we've got is a situation where Bernoulli's equation demands that if the velocity goes up, the pressure has to go down. And in fact, the pressure decreases so much that it dips from the positive. The pressure was above the atmospheric pressure, but then it actually goes down between these two lines, lower than atmospheric pressure, but it's not down to zero vacuum of space yet. If it goes fast enough through that contracted throat, these little vapor bubbles will start to form. And it's not because the liquid's hot, it's not heating up inside of that contracted throat section, it's because the surrounding pressure of the water is so low in here that the water begins to boil. It goes from the liquid phase to the vapor phase simply because the surrounding pressure is so low. So we have an illustration here where it asks what is going to be the pressure in this contracted throat section, and will the water cavitate? So let me go through those calculations quickly. We don't have a lot of time, but I think we'll have enough to find out, will the system experience cavitation? At 1, we know the pressure, and this is the absolute pressure. I'll have to note that this isn't the gauge pressure, this is the absolute. We know the velocity at both locations. The question is, what's the pressure at 2? We're going to use Bernoulli's equation as our way of predicting what the pressure change is going to be. Okay, Z1 and Z2 are equal because that's on the same horizontal plane. And we'll just substitute in the known pressure, 814,000 newtons per meter squared, divided by the unit weight, 9643 newtons per meter cubed. And that's a strange number, right? Well, it's because it's 60-degree water. It's warm water, which is a little bit more risky for cavitation because the vapor pressure of warm water is higher than the vapor pressure of cool water. Plus 0 for the elevation, plus 20 meters per second squared, divided by 2, 9.81 meters per second squared, is equal to P2, 9643 newtons per meter cubed, plus 0 plus 45 meters per second squared, divided by 2G. This is 84.41 meters. The velocity head is 20.39 meters. The velocity head at 2 is 103.21 meters. So P2 is 1.59 meters of head times 9,643 newtons per meter cubed. That means that the pressure of the water at location 2 is only going to be 15,332 newtons per meter squared, and that is less than the vapor pressure. P sub V is greater than P2, so yes, there's cavitation. When we get together in class on Thursday, we'll talk about why cavitation is risky and look at some pictures of the damage that it can cause. So I'll see you all at 2 o'clock for lab. We're going to meet back in the lab area. Just grab a chair and we'll talk about the experiment that you've got for this week and next.